Okay, so in the last lecture we had stopped at the definition as well as the basic equation of AM for a single tone case. Okay, now we shall try to see the time domain representation of it and see what are all the components we get. Okay, so when you try to expand this S of t equation that is written above, that is this equation. Okay, just hold on for a while. So let me use a pen. So if you try to see this equation, and if you expand that equation, what you get is basically, okay, just hold on for a second. Okay, if you see this equation here, yeah, if you see this equation and if you try to expand it, this is the equation what you basically get, where S of t is equal to EC or AC into cos of omega ct plus mu, which is equivalent to m AC into AC by 2 into cos of 2 pi fc plus 2 pi fm into t. Quite interesting, we are able to get something here, plus mu or ma into AC divided by 2 into cos of 2 pi fc minus 2 pi fm into t. So what you observe is there are three components here. Okay, number one is this fellow, number two is this, number three is this. What is the frequency of the first component? It is fc, isn't it? Second, it's fc plus fm. Third is fc minus fm. So fc is anyways the carrier. The other two components what you see, which is fc plus fm and fc minus fm, they are called the upper sideband and the lower sideband frequency components. And this is what you observe when you try to perform a amplitude modulation. So you will get two different components apart from the carrier. So in total there will be three components in a amplitude modulated wave. Okay. Okay, so now we shall see what is the frequency domain representation of this. Okay, so when I try to take the Fourier transformation of this signal, S of t equals AC cos 2 pi fct whole multiplied by 1 plus ma into cos 2 pi fmt, I get this equation. Okay, and what is that equation? The equation is right in front of you here. Fine. Okay, so which is AC by 2 into delta of f minus fc plus delta of f plus fc, because cos 2 pi fct delta, Fourier transformation is delta of f minus fc and delta of f plus fc divided by 2. Okay, that's basically the Fourier transformation of a cos, and sign will be, you will have a complex for the second term with a negative sign. Okay, so when you expand it, this is what you get. So what you will have is a component of delta with a frequency fc or at a frequency fc, and AC MA divided by 2 into M of f minus fc plus M of f plus fc. So M basically stands for the modulating signal spectrum, M of f minus fc, but it's a shifted version of M of f, shifted by an amount of fc to the right, shifted by an amount of fc to the left. And what you observe is this kind of frequency response. Where is it? Right here. So this is what you basically get. Okay, so this is how will the frequency response of an amplitude modulated wave will look like. So this is case of a a multi-tone signal. If you take a single tone signal, the spectrum will look like this. So let me write it this way. Okay, so what you will have is this kind of spectrum. So this center frequency will be fc, this will be fc plus fm, this will be fc minus fm, and you will also have frequency components which are mirror images in the negative axis of frequency, which will not have any significance, but the Fourier makes us to write all those components. Okay.